Welcome back. This will be a video lecture on section 4.3 of the textbook, Eigenvalues and Eigenvectors of n by n matrices. I've broken this section up into two parts, computing eigenvalues and some additional theory. So let's begin with computing eigenvalues. Now the key to computing eigenvalues rests on the equivalence of the following five statements. Let A be a square matrix. The following are equivalent. Statement number 1, lambda is an eigenvalue of A. Statement number 2, there exists a non-zero vector V such that the matrix A minus lambda I times the vector V equals the zero vector. Statement number 3, the null space of the matrix A minus lambda I does not consist of just the zero vector. Statement number 4, A minus lambda I is not invertible. And finally, statement number 5, the determinant of A minus lambda I is equal to 0. Now, back in section 1 of chapter 4, we saw the equivalence of these four statements. By the time we finished section 2, we saw that in general for an n by n matrix, a matrix is not invertible precisely when its determinant is equal to 0. And this gives us the key to computing eigenvalues in general. We can simply look for places where, or values lambda, where the determinant of A minus lambda I is equal to 0. Now let's put this idea to work. Let's work the following problem. Find the eigenvalues and corresponding eigenspaces of the 3x3 matrix A. I'll see you at the document camera to work out the details of the solution to this problem. All right, welcome to the document camera. In this problem, we have to find all of the eigenvalues of the matrix A, and for each eigenvalue, we have to work out the corresponding eigenspace. Now, in principle, we know what to do. We form the matrix A minus lambda I, and that is simply what we get, the matrix we obtain by subtracting lambda from each of the diagonal entries of A. We have to calculate the determinant of A minus lambda I. That's the so-called characteristic polynomial of A. And then we have to find the roots of that characteristic polynomial. Those will be the eigenvalues of the matrix A. Now, I'll spare you the details, but we have to calculate the determinant of A minus lambda I. And I will just show you, and you can check me on this. This is equal to the cubic polynomial in lambda, namely negative lambda cubed plus 2 lambda squared plus lambda minus 2. Now, we have to find the roots of this cubic polynomial, and that in general can be a hard problem, but in this case it's actually rather easy because this factors nicely as a negative 1 times lambda minus 2, lambda minus 1 times lambda plus 1. So when we set that equal to 0, we can see we're going to have roots corresponding to lambda equals 2, 1, and negative 1. So this is the complete set of eigenvalues corresponding to this matrix A. This is the so-called spectrum of the matrix A. Now, there's still a lot of work ahead of us because what we have to do now is for each of these eigenvalues, we have to form the matrix A minus lambda I. So in particular, A minus 2I. And then we have to row reduce that matrix and work out a basis for the null space of that matrix. Let's do this in some detail for the case lambda equals 2. So when lambda equals 2, we have to start with the matrix A minus 2I. Now we know what to do. We're just going to plug in lambda equals 2 here. And that's going to give us the matrix consisting of 6 minus 2, or 4, negative 8, negative 14, negative 1. Here we'll have 1 minus 2, or negative 1, 2, 2, negative 4, and then negative 5 minus 2, so negative 7. Now, we're looking for homogeneous solutions to the equation A minus 2I times some vector x equals the zero vector. Now, we can just imagine augmenting this with a column of zeros and doing the steps to row reduce this to work out the homogeneous solutions, or the null space of A minus 2I. So let's just go ahead and imagine tacking on that column of zeros, but we're going to basically row reduce this matrix. Now, when we row reduce this matrix and put it into its reduced row echelon form, the matrix we end up with looks like this: 1, 0, negative 5 halves, 0, 1, 1 half, and 0, 0, 0. Okay, now we're looking for homogeneous solutions, so let's call our variables x1, x2, and x3. We can see that the variable x3 is going to be a free variable, and x1 and x2 will be bound variables. And so we can read this top equation. Well, let's set x3 equal to s. And so this top equation is telling us that x1 minus 5 halves of s is equal to 0, or x1 is equal to 5 halves s. The second equation is telling me that x2 plus 1 half of s is equal to 0, so x2 is equal to a negative 1 half of the variable s, the free variable s. So any solution to the homogeneous equation is going to have the form x1, x2, x3 is equal to 5 halves s, negative 1 half s, and s. Now, I'm trying to work out a basis for the null space. And what I'm going to do is show that, obviously we only have one dimension here, so we have to find a direction vector that will specify this null space. And one way to do this is just to pull s out and take the vector that remains. So we could think of this as s times 5 halves, negative 1 half, and 1. Okay, and that would form a basis vector for E sub 2. You get a nicer looking basis vector if instead of just pulling out s, you pull out 1 half s. And so it's sometimes nicer to have a nicer representation for your basis vector. And so what I'm going to do here, instead of just factoring out s, I'm going to factor out s over 2, a half of s. So what I'd rather do is write this as 1 half of s times 5, negative 1, and 2. This shows me that any solution to the homogeneous system is just some scalar times 5, negative 1, 2. And so I'm going to write E sub 2 as the span of 5, negative 1, and 2. So the eigenspace corresponding to lambda equals 2 just consists of all multiples of the vector 5, negative 1, and 2. And that's a nice way to represent E sub 2. Now, the same kind of work would ensue for lambda equals 1 and lambda equals negative 1. And so let me just cut to the chase. If you go ahead and do this work, the same work, now for lambda equals 1 and lambda equals negative 1, here's what you're going to find. The eigenspace corresponding to E sub 1, the eigenspace corresponding to lambda equals 1, consists of the span or all multiples of the vector 4, negative 1, and 2. And E sub negative 1, the eigenspace corresponding to lambda equals negative 1, is going to be the span of the single vector 2, 0, and 1. Okay? And so there's our eigenspaces that correspond to each of our eigenvalues. In each case, we have a one-dimensional eigenspace, or a one-dimensional null space, if you will. All right, so in principle, That's how we can take a 3 by 3 matrix, find its complete list of eigenvalues, and then work out the eigenspaces corresponding to each of those eigenvalues. Now, let's head back to the document camera, or let's head back to the class notes. Now, with regard to eigenvalues and their corresponding eigenvectors, we want to make a distinction between the algebraic multiplicity of an eigenvalue and the geometric multiplicity of an eigenvalue. And the best way to see this is by looking at an example. So here we have a 4 by 4 matrix A. When we calculate its characteristic polynomial, namely the determinant of A minus lambda I, we see that it factors nicely into lambda minus 3 squared times lambda minus 1 squared. So there are only two eigenvalues for this matrix A, namely lambda equals 1 corresponding to this factor and lambda equals 3 corresponding to this factor. Now, because lambda minus 1 appears to the power of 2, we say that lambda equals 1 has an algebraic multiplicity of 2. So the algebraic multiplicity is merely recognizing that in this case lambda minus 1 is appearing to the power of 2. Likewise, we would say that lambda equals 3 has algebraic multiplicity 2 because lambda minus 3 is appearing also to the power of 2. So the algebraic multiplicity merely tells you what the power of the corresponding factor is in the factorization of the characteristic polynomial. Now let's compare the notion of algebraic multiplicity with that of geometric multiplicity, and let's begin by looking at the eigenvalue lambda equals 1. Now the geometric multiplicity of lambda equals 1 is the dimension of the corresponding eigenspace E1. And so the first thing we have to do is we have to take the matrix A minus 1 times I and row reduce it. And when we do that, we discover that there are two free variables present, and therefore the dimension of E1 is 2, and the geometric multiplicity of lambda equals 1 is therefore 2. Now let's compare this with the eigenvalue lambda equals 3. When we take A minus 3 times I and row reduce it, we find that there is only one free variable, and therefore the dimension of E3 is going to be 1, and so the geometric multiplicity of lambda equals 3 is 1. Now, if we summarize our findings, here's what we find, right? The characteristic polynomial of that matrix A has two eigenvalues, namely lambda equals 3 and lambda equals 1. And since lambda minus 3 appears to the power of 2 and lambda minus 1 appears to the power of 2, that accounts for the algebraic multiplicities that we see here corresponding to each of these eigenvalues. On the other hand, we found that the dimension of the eigenspace E1 is 2, while the dimension of the eigenspace E3 is only 1. And so we find that the geometric multiplicities are 2 and 1 accordingly. And so this is a possibility. The algebraic multiplicities and the geometric multiplicities of eigenvalues do not have to agree. Now, what we'll find is that the geometric multiplicity will always be less than or equal to the corresponding algebraic multiplicity. But as this example shows, in the case of lambda equals 3, the geometric multiplicity can come up short of the corresponding algebraic multiplicity. Now let's study some additional theory, and we'll begin with theorem 4.15. The eigenvalues of a triangular matrix are the entries on its main diagonal. Now let's study this example. Here's a matrix A, a 3 by 3 matrix, which is upper triangular, and the elements on its main diagonal are 2, -3, and 1. Now, if we want to calculate the eigenvalues of this matrix, we would subtract lambda times the identity matrix from A, and that would have the effect of subtracting lambda from each of its diagonal elements. The key observation is this: A minus lambda I is still upper triangular, and that means when we compute its determinant, we're simply going to get the product of its diagonal elements, and that's going to be 2 minus lambda times -3 minus lambda times 1 minus lambda. Now what we're seeing here is that the determinant of A minus lambda I, in other words, the characteristic polynomial of A, is already coming to us in factored form, and we can read out its roots immediately, namely lambda equals 2, lambda equals -3, and lambda equals 1. In other words, the roots of the characteristic polynomial, the eigenvalues of A, are simply the elements on the main diagonal of A. And that's what theorem 4.15 is asserting, that what we're seeing here in this example is true of any triangular matrix. Our next two main theorems, theorem 4.16 and theorem 4.17, both rest on the equivalence of the following 5 statements. Now, statement 1 says 0 is not an eigenvalue of the matrix A. Now, that's equivalent to the statement that the null space of A minus 0 times the identity matrix consists only of the 0 vector. And that statement is equivalent to the statement that the null space of the matrix A consists only of the 0 vector. And by our fundamental theorem of invertible matrices, the null space of A equaling the 0 vector, or consisting only of the 0 vector, is equivalent to A is invertible. And finally, by our work of section 4.2, A is invertible is equivalent to the statement that the determinant of A is not equal to 0. Now, if we look at theorem 4.16, it's drawing out this implication. A square matrix A is invertible if and only if 0 is not an eigenvalue of the matrix A. And if we look at theorem 4.17, this is just an extension of the fundamental theorem of invertible matrices, and they're calling this version 3. Now, we've already seen the equivalence of statements A through M at various times in this course. What we're doing here in version 3 is we're tacking on 2 final statements. Statement N says the determinant of A is not equal to 0, and statement O says that 0 is not an eigenvalue of A. Now, we've just seen that 0 is not an eigenvalue of A is equivalent to A is invertible, and the determinant of A is not equal to 0. And so we can add entries N and O to the fundamental theorem of invertible matrices. Now, our next main theorem, theorem 4.18, says let A be a square matrix with eigenvalue lambda and corresponding eigenvector x. Now, statement A says for any positive integer n, lambda to the n is an eigenvalue of A to the n with corresponding eigenvector x. Statement B says that if A is invertible, then 1 over lambda is an eigenvalue of the inverse of A with corresponding eigenvector x. And statement C says that if A is invertible, then for any integer n, positive or negative, lambda to the n is an eigenvalue of A to the n with corresponding eigenvector x. Let's go to the document camera and work out the proof of theorem 4.18. All right, welcome to the document camera. We're going to look at the proof of theorem 4.18. And in this theorem, we've got a square matrix A with an eigenvalue of lambda and a corresponding eigenvector of x. And so let's write out that relationship. We know that when we take the matrix A and apply it to that vector x, that we're going to get a multiple of that vector x, namely lambda times x. And so that's kind of like a statement of fact that's present in all of the parts of this theorem 4.18, that A applied to x always equals lambda times x. Now, what we want to show in part A is that lambda to the power of n is an eigenvalue of A to the power of n for that same eigenvector x. Now, one way to see this is just kind of to work up to it by steps. So if this relationship is true, right, then I can apply the matrix A to both sides, both the left-hand side and the right-hand side, and obtain another true statement. So I can apply the matrix A here and here. Let's see what we get. Now on this side, I can use associativity and write this as A squared applied to x. On this side, I can use linearity of this transformation. I can pull the lambda through and think of this as lambda applied to ax. But ax is just the lambda times x, and so this is simply lambda squared times x. So a squared applied to the eigenvector x is lambda squared applied to x. So that says that x is an eigenvector for the eigenvalue of lambda squared. So a squared has lambda squared as an eigenvalue with corresponding eigenvector x. Now, we can do this again. I can apply the matrix A to both sides. This side will become a cubed. On this side, I'll be applying the matrix A to lambda squared times x. Once again, I can pull that scalar through using linearity. And now I can look at ax and I can realize that's just another lambda times x. And so this is going to be simply lambda cubed times x. So lambda cubed is an eigenvalue of a cubed with that same eigenvector x. Well, you can see how we could iterate this, right? We could keep iterating this. We could work this out for the 4th power, the 5th power, the 6th power. In general, for any positive power n, we would know that a to the n applied to x is going to equal lambda to the n applied to x. And so that gives us this relationship that we were looking for in part A. We can see that lambda to the n is an eigenvalue of a to the n with eigenvector x. And so that fulfills part A of theorem 4.18. Now, part B asks us to consider the case where A is invertible and to show that 1 over lambda, lambda to the minus 1 if you will, is an eigenvalue of a to the minus n, a to the minus 1, the inverse of a, with corresponding eigenvector x. And so let's take a look at that relationship. Now, let's call this part A. We're in part B now. We're going to begin again with this relationship, ax equals lambda times x. And what we're going to do is we're going to multiply both sides of this relationship by the inverse matrix A inverse. Now, what can we do? On this side, we can reassociate and think of this as A inverse times A applied to x, but A inverse times A is the identity, and the identity matrix times x is just x. So on this side, we're simply going to have the vector x. On this side, we can pull the scalar lambda through because A inverse is itself just another matrix and it's linear, so I can simply write this as lambda times A inverse applied to x. Okay, now here's where we have to just bring in one more fact. We know that A is considered in part B, A is considered an invertible matrix. It has an inverse. We've used that fact already. But we now need to know one more thing, and we've actually already looked at this. We have to know that when A is invertible, if lambda is an eigenvalue of A, it can't be equal to 0. So lambda, we know for sure that since lambda is an eigenvalue for this matrix A, and since the matrix is assumed to be invertible, we know for sure that lambda is not equal to 0. Now that's an important step here because what I'm going to do is divide both sides by lambda or equivalently multiply both sides by 1 over lambda. So we can write this relationship as A inverse applied to x is equal to 1 over lambda times x. And when we write it this way, we can see that 1 over lambda is clearly an eigenvalue for the matrix A inverse with corresponding eigenvector x, the same eigenvector that we've been working with from the beginning. So that same eigenvector is now an eigenvector for the matrix A inverse corresponding to eigenvalue 1 over lambda. Now, I think a better way to write this relationship, just because it's so suggestive when we get into part C, is to write this relationship as A inverse x is equal to lambda to the minus 1 times x. That's a better way to think of the relationship here. Okay? Now we get to part C. Now part C is asking us to show that if A is invertible, then for any integer n, lambda to the n is an eigenvalue of A to the n with corresponding eigenvector x. Now, this sounds suspiciously like part A, right? It sounds just like what we proved in part A, except the hitch is this, right? This is also applying, we've already covered that case when n is a positive integer. This is now really especially asking us to think about proving this statement when n is a negative integer, all right? So for instance, a to the negative 3 or a to the negative 10. In general, what do we do with a negative integer power of a? We have to show that lambda to that same negative integer power is an eigenvalue with this same eigenvector. Now, here's what I want to do. I want to let n be a positive integer. And what I want to do is I want to look at this through the lens of thinking about a raised to the power of minus n. So I want to think of a raised to the power of minus n. So this would, for instance, be a to the negative 8 or a to the negative 10, where n could equal 8 or 10. So a raised to the power of minus n applied to this vector x. I want to show that this is equal to lambda raised to the power of minus n times the vector x. And here's the way we're going to do it. Here's a way to do it. Remember that we can always think of a raised to the power of minus n as a inverse raised to the power of n. Okay? Now what do we know? We know that a inverse is a matrix, and n is now a positive power. And we've already showed in part A that when I take a matrix that has a known eigenvalue with corresponding eigenvector, and I raise it to a power, that I get the eigenvalue that corresponds to that eigenvalue raised to that same power, and that this is still an eigenvector for that eigenvalue. So I'm basically leveraging part A of our argument now for the matrix A inverse. All right? And so using part A now here in part C, but now applying it to the matrix A inverse, we can conclude that this is equal to lambda to the minus 1 raised to the power of n times x, or equivalently, lambda to the minus n times x. Okay? So once again, I'm using part A of this theorem, but applying it to the matrix A inverse. All right. So we get this relationship. And that shows us that the matrix A to the minus n has an eigenvalue of lambda to the minus n with eigenvector x, the same eigenvector that we've been working with all along. All right, and that almost proves part C. The only gap that we have in our proof is what do we do in the case where n is equal to 0. So we've got all the cases where n is greater than or equal to 1 here. This would give us all the cases where n is less than or equal to negative 1 here. Those are all covered here, the purely negative powers of A. But what about the case where n is equal to 0? And let's just remember that a to the 0 is the identity matrix. So when I look at a to the 0 times x, that's the same thing as the identity matrix times x. And that's just equal to x. But I can always write x as lambda to the power of 0 times x. So even in the case where the power in this case is equal to 0, I can see that a to the 0 has eigenvalue lambda to the 0 with corresponding eigenvector x. And so what this shows, when we put part C together with part A, we can show that if a matrix is invertible, and it has an eigenvalue of lambda and corresponding eigenvector x, then any power of the matrix that I would take, if I would take a to any power, positive or negative, it's going to satisfy this relationship. Lambda to the n will be an eigenvalue of that matrix with corresponding eigenvector x. And so that concludes part C of theorem 4.18. Now this is a very important theorem because many problems in matrix, especially applications of matrices, involve the study of powers of a matrix, and we'll see that this becomes a very important consideration in what we're about to do, especially in section 4.4. So hopefully you've learned something from this theorem 4.18, and let's head back to the class notes and continue. Now our next problem is going to point us in the direction of our next two theorems, theorem 4.19 and theorem 4.20. So let's recall that the matrix A, this 3 by 3 matrix, has eigenvalues lambda 1 equals 2, lambda 2 equals -1, and lambda 3 equals 1, with corresponding eigenvectors x1, x2, and x3. Now, in part 1 of this problem, let's show that these eigenvectors, x1, x2, and x3, form a basis for R3. In part 2, let's take a vector in R3, in this case consisting of components 10, -3, and -6, and let's express v in the coordinates given by the basis consisting of x1, x2, and x3. So let's find the coordinates of this vector v relative to that basis, and then let's use that representation of the vector v to conveniently work out, let's say, the 10th power of the matrix of A applied to the vector v. We'll show how we can use the power of this representation of the vector v to quickly work out the 10th power of A applied to the vector v. So join me at the document camera to work out the details of the solution to this problem. All right, welcome to the document camera. In this problem, we've got this matrix A, and this should look familiar to us because this is the matrix we worked with earlier in the section. There we saw that the matrix A had eigenvalues 2, -1, and 1, and some corresponding eigenvectors 5, -1, 2, 2, 0, 1, and 4, -1, 2. Now, we've got two problems to work out here corresponding to this matrix A. Our first task is to show that these eigenvectors collectively form a basis for R3. So that's step 1. And in principle, we know what to do. We're going to simply feed these vectors in as the columns of a 3 by 3 matrix. So we'll have 5, -1, and 2, 2, 0, and 1, 4, -1, and 2. And then we're going to take this matrix down to its reduced row echelon form. In this case, I've done this work ahead of time. When we row reduce this matrix, it row reduces to the identity matrix. And one of the consequences of our fundamental theorem on invertible matrices is that if a matrix row reduces to the identity matrix, then its columns, in this case, are forming a basis for R3. So we can say that the collection of vectors B consisting of x1, x2, and x3 form a basis for R3. Okay, so we've fulfilled the first part of this problem. Now in the second part of the problem, we've been given a very specific vector. In this case, the vector v has components 10, -3, and -6. And we've been asked first to work out the coordinates of v relative to this basis. So notationally, we're being asked to compute the coordinates of v relative to b. But we can think of this as a spanning problem, right? Really, this is just asking us to find the coefficients of x1, x2, and x3 such that the linear combination, the corresponding linear combination of x1, x2, and x3 would bring us to this vector v. Now, we know that there is a unique set of coefficients that will do this. That's what it means. That's one of the consequences of being a basis, is that there is a unique set of coefficients that will produce from x1, x2, and x3 will produce this vector v. We just have to find them. Now, that's a familiar problem to us. That's just a spanning problem. And so we know, again, in principle, what to do. We're going to feed our basis vectors in as columns. And we'll augment this by the vector v. and we'll take this down to its reduced row echelon form. Now, we could equivalently do this problem by matrix inversion, but this is simple enough. We're going to row reduce this. And again, not surprisingly, on this left-hand side, we're going to get the identity matrix. That's to be expected. Now, what we're looking for, and here's where everything is, we want to know what is sitting in this augmented column. We're going to have 22, a negative 12, and a negative 19. And so that's going to tell us exactly the coefficients that we should use on x1, x2, and x3. So there's a couple of different ways we could express this. We could say that the coordinates of v relative to the basis v consist of 22, negative 12, and negative 19. But for the purposes of what we're about to do, it's better just to think of what we've done is we've shown that v can be expressed as 22 times x1 plus negative 12 times x2 plus a negative 19 times x3. You'll see, for the purposes of where we're going, that although this is true, this is a better way to think about what we're doing. We've got the vector v now expressed in terms of this basis x1, x2, and x3 using those coefficients. Now, our last task is to take the 10th power of this matrix A and apply it to the vector v and work out the solution to that problem. So we have to kind of find a nice way to express the 10th power of the matrix A applied to that vector v. Now what we can use is we can use the fact that the 10th power of this matrix is itself a matrix. And we can use basic properties of matrices, or if you will, basic properties of linear transformations, to know that when we apply this 10th power of A, it's going to distribute across this sum, and we can pull all of these scalars through. So the 10th power of A applied to V is the same as 22 times the 10th power of A applied to x1. Negative 12 times the 10th power of A applied to x2, and a negative 19 times the 10th power of A applied to x3. And now here's the magic, right? Here's where it really pays to now be working with some eigenvectors. The theory tells us that x1 is an eigenvector for the matrix A, and that means x1 is also an eigenvector for the matrix A to the 10th. But now with eigenvalue 2 to the 10th. And so this is simply going to be 2 to the 10th times x1. Now likewise, x2 is an eigenvector for A, and that means it's an eigenvector for A to the power of 10 as well, but now with eigenvalue negative 1 to the 10th. And finally, using exactly the same logic, x3 is an eigenvector for A, and therefore it's an eigenvector for A to the 10th, but now with eigenvalue 1 raised to the power of 10. Okay. And so what we've seen is that even though we have to, in some sense, solve a problem like what is the 10th power of a matrix A applied to a vector, it turns out that that's actually very easy to do when you're working with an eigenvector of the original matrix A. So this is where we're really gaining something by having eigenvectors here. When we finally work out, for example, the 10th power of A applied to x1, the 10th power of A applied to x2, and the 10th power of A applied to x3, having eigenvectors here greatly simplifies the next phase of that calculation. Now, let's just see where this is going, just to get a feel for where this is going. 2 to the power of 10 is 1024. So this would be times x1. So there's our coefficient of x1. A negative 1 to the power of 10 is just 1. So this is just going to be negative 12 times x2. And then 1 to the power of 10 is just 1, so this will be a negative 19 times x3. Now, let's just step back and ask ourselves, what if instead of the 10th power we had the 100th power, or in general, the nth power of a? How would we express the nth power of a applied to our vector v? What would that look like? Well, we can see exactly where the change is going to appear. Instead of having the 10th power of 2 here, we'd have the nth power of 2. We'd have the nth power of negative 1. We'd have the nth power of 1. So in general, if I needed to compute an arbitrarily large power of a applied to our vector v, we know in principle what it would look like. It would have 22 times 2 to the nth times x1. We'd have negative 12, negative 1 to the nth times x2. And then finally, we'd have negative 19, 1 raised to the power of n times x3. And now many problems in matrix analysis turn into questions like this. What happens to the a to the power of n applied to v as n goes to infinity, as n gets larger and larger? What's going to happen? Well, one thing we observe in this case is that this 1 to the power of n is just always going to equal 1, so we're just going to have negative 19 times x3 tacked on at the end. This negative 1 to the n here is just going to flip-flop between 1 and minus 1, so this will either be negative 12 times x2 or positive 12 times x2. Here's the telling part, though. As n gets bigger and bigger, this part is going to grow exponentially. It's 2 to the power of n. And so what we can see, right, is that for this particular problem, because this matrix has eigenvalues 2, negative 1, and 1, we can see that as n gets arbitrarily large, a to the n times v is going to be asymptotically very similar to just 22 times 2 to the power of n times x1. This is going to be dominating the behavior of a to the n times v as n goes to infinity. And in many scenarios, that's exactly what you're trying to study. So if a was pertaining to some Leslie matrix governing population growth, we would know roughly what's happening to our population. Given some initial state for that population, we would know roughly how that population is growing, the rate with which it's growing as n is going to infinity. It's going to be governed by the largest eigenvalue in our matrix. Okay, so let's head back to the class notes and pick up on this theme. Our next theorem, Theorem 4.19, is a generalization of what we saw in our previous problem. Suppose the n by n matrix A has eigenvectors v1 through vm, with corresponding eigenvalues lambda 1 through lambda m. If x is a vector in Rn that can be expressed as a linear combination of these eigenvectors, so let's say that x can be expressed as c1 times v1 plus c2 times v2 on out to c sub m times v sub m, then for any integer k, the kth power of the matrix A applied to the vector x can be written as a linear combination of the vectors v1 through vm, now with coefficients c1 times lambda sub 1 to the k, c2 times lambda sub 2 to the k, on out to c sub m lambda sub m to the power of k. And this is exactly what we saw in the result of our previous problem. Now our next and last theorem, Theorem 4.20, is very important, especially as we move into section 4.4. Now let A be an n by n matrix, and let lambda 1 through lambda m be distinct eigenvalues of A with corresponding eigenvectors v1 through vm. Then the eigenvectors v1 through vm are linearly independent. Let's go to the document camera and look at the proof of Theorem 4.20. All right, welcome to the document camera. Let's look at the proof of Theorem 4.20. Now, I'm going to do a simplified version of this theorem. I'm going to assume that we've got three distinct eigenvalues, lambda 1, lambda 2, and lambda 3. Now these are eigenvalues of the same matrix A. And we have corresponding eigenvectors v1, v2, and v3. Our job is to show that v1, v2, and v3 are linearly independent. And so what we're going to do is just do the usual thing. We're going to look at a linear combination of v1, v2, and v3, set it equal to the zero vector, and show that we're forced to use the trivial coefficients. In other words, the only way to span the zero vector with v1, v2, and v3 is to use trivial coefficients. All right, so let's call the coefficients a1, a2, and a3. So we're going to look at a1 times v1, a2 times v2, and a3 times v3. We're going to set that equal to the zero vector and see what kind of solutions for a1, a2, and a3 that there are. Now, here's the inspired bit. What we're going to do is I'll show you how we can demonstrate, for example, that a1 has to be equal to 0. The same argument with the obvious modifications will be used to show that a2 must equal 0 and that a3 must equal 0. So you'll see that the argument that I'm using to show that we're forced to conclude that a1 is equal to 0 could be modified in an obvious way to show that a2 and a3 would have to be equal to 0. And this relies ultimately on the fact that these eigenvalues are distinct from each other. These are not repeats. Okay, so here's the way the argument works. First, we're going to apply the matrix A to both sides of this equation. All right? And when we apply the matrix A to this side, we can use the linearity of the matrix to show that it's equal to A1 times capital A applied to V1, A2 times capital A applied to V2, and A3 capital A applied to V3. But V1 is an eigenvector, and so that's just going to be lambda 1 times V1. We'll have a lambda 2 times V2 and a lambda 3 times V3. So once again, I'm applying a matrix A to both sides, the matrix A to both sides of this, and I'm strongly using the linearity of the matrix and the fact that v1, v2, and v3 are eigenvectors for that matrix with corresponding eigenvalues lambda 1, lambda 2, and lambda 3. So apply A to both sides, use these properties. What we end up with is an equation that looks like this. A1 lambda 1 times v1, A2 lambda 2 times v2, and A3 lambda 3 times v3. And that's going to have to equal what I get when I apply A to the zero vector, which is just 0. All right, so that's step 1. Now step 2 is to take this first equation and multiply it by lambda 2. So just multiply both sides of this equation by lambda 2. So what we end up with is A1 lambda 2 V1 plus A2 lambda 2 V2 plus A3 lambda 2 V3 is equal to 0. Okay? So this is the result of applying A to both sides, and this is the result of multiplying both sides, in this case, by lambda 2. Now, this gives us a pair of equations. Let's call this one equation 1 and this one equation 2. Now, what I want to do is take equation 2 and subtract equation 1. All right. Now, what we'll see, and this was part of the method for multiplying this equation here by lambda 2, what I'm trying to do is effectively eliminate A2 from this equation. So when I take equation 2 minus equation 1, on this left-hand side, I'm going to have A1 times lambda 2 minus lambda 1 times the vector V1. These two will cancel each other, and then I'll have this difference. I'm going to have A3 lambda 2 minus lambda 3 times the vector V3. And that's going to equal 0 minus 0, or 0. All right? So that's our first reduction. We've gotten the vector V2 out of the equation. And now we're going to do this once again. We're going to do a multiplication by the matrix A, and then we'll do a scaling by, in this case, lambda 3. And you'll see that that's going to help us eliminate this coefficient and vector v3 from this equation. All right, so here's how this works. Let's apply the matrix A now to both sides of this equation. We're going to use the fact that A is linear, and when I apply A to v1, I get lambda 1 v1, and when I apply A to v3, I get lambda 3 v3. So this, applying A to both sides of this equation will give us A1 lambda 2 minus lambda 1, lambda 1 v1, A3 lambda 2 minus lambda 3, lambda 3 v3. And that has to equal 0. Now I'm going to multiply both sides of this equation by lambda 3. So I'll have a lambda 3 here and a lambda 3 here. So once again, I got this equation by multiplying my base equation by the matrix A, and I got this equation by multiplying my base equation by lambda 3. Now, I'm going to take the difference again. We can think of this as our new equation 1 and our new equation 2. I'm going to take the difference, 2 minus 1, again, just as before. All right, when I take the difference, I can see that this part's going to cancel. Those are equal to each other. So what I'm going to get here is A1, lambda 2 minus lambda 1, lambda 3 minus lambda 1. The vector V1 is equal to the 0 vector. Now here's what we just have to, here's the end game, if you will, right? This scalar is multiplying the vector V1 to get the 0 vector. Now here's one thing we know. We know that V1 is not the 0 vector. That's a hallmark property of an eigenvector. An eigenvector is never the 0 vector. So we know that V1 is not the 0 vector. So the only way that this scalar times this vector can equal the 0 vector is if this scalar is equal to 0. So we know that A1 times lambda 2 minus lambda 1 times lambda 3 minus lambda 1 must itself be equal to 0 as a scalar. Now here's where it's crucial that we understand that these eigenvalues are not repeating. These are all distinct eigenvalues. And that means in particular that lambda 2 minus lambda 1 is not equal to 0. And that lambda 3 minus lambda 1 is not equal to 0. And so the conclusion that we're forced to draw is that A1 itself must be equal to 0. One of these three numbers has to be equal to 0. It's not this one. It's not this one. It must be that one. A1 is equal to 0. Now, making the obvious changes, you can go through the same argument again and show that we must conclude that A2 is equal to 0 and that A3 is equal to 0. So what we're forced to conclude is that if we want to use V1, V2, and V3, if we want to use those to produce the 0 vector, we're forced to use A1 equals A2 equals A3 equals 0, and therefore the collection V1, V2, and V3 is linearly independent. And that's what we wanted to show. The argument for a collection of M vectors is not that different. Okay, it really wouldn't be that much different. It would be a lot more rigmarole to go through the entire argument, but it's not any different conceptually than what we've done here for these three vectors. All right, so hopefully you've gained some insight into the meaning of Theorem 4.20 and how it works. We're going to make extensive use of this idea when we go into section 4.4. So hang on to this. This is an important thought. We'll make use of this when we get into section 4.4. Now that concludes our work here in section 4.3. So I'll ask you to join me again when we work through a video lecture on section 4.4. Until then, take care. Bye-bye.